Welcome to the ChemDoctor, and this video is going to focus on calculating the molar mass of a hydrate. I've produced other videos that deal with naming these particular types of compounds, and so what I'll do right at this moment is just briefly review what they are. So a hydrate is an ionic compound that is complex to a certain number of water molecules. And to start, what I want to do is draw your attention to the compound up here on the left. This particular compound is otherwise known as Epsom salt. And you'll notice that in a hydrate, you can break the formula down into basically two parts. There is the part that gives us the formula of the ionic compound. In this case, that's the magnesium sulfate. Then there's the part that deals with the hydrate issue, which is the number of water molecules that are complex to the ionic compound. Now, how do we read and how do we use this formula? So the first thing is, in terms of the naming, the naming of the ionic compounds in each of these cases is no different than what we've done before. So in other words, if the cation that's part of the ionic compound is out of group 1 or 2, or it's a triad being either zinc, aluminum, or silver, then we do not use a Roman numeral in the naming. You need to pay attention to the type of polyanion that is part of the ionic compound because we're going to use its name. So for this compound, for Epsom salt, the name of the ionic compound will be magnesium sulfate, and then we need to deal with the H2Os. So in the case of the H2O, we're going to use the word hydrate, and then we need to deal with this number. Now you'll notice that in the formula there's a dot, and oftentimes students look at this dot and they misunderstand it. They take it to mean from mathematics that we're multiplying the ionic compound times the H2Os that appear on the right side here, and that would be incorrect. The dot actually means, and I think I'm going to put it in here, it means you can attach the word "and" to this. So it essentially means addition. All right, we're going to be adding whatever the molar mass is of the ionic compound to the molar mass of however many water molecules we have that are attached to it. So an ionic hydrate is simply an ionic compound that's complex to a certain number of water molecules. And if we need the molar mass, what we're going to do is calculate the molar mass of the compound, and then we're going to add to that the molar mass of however many H2Os we've got that are attached to the compound. So in this case, you see that there are 7 of them. So in the naming, we're going to use the word hydrate to indicate the water, and then that just leaves us with a way of indicating how many water molecules there are that are attached to this. And we're going to use a Greek prefix for that part of it. So in the case of the 7, we're going to use the prefix hepta. So this hydrate becomes magnesium sulfate heptahydrate. All right, now let's go ahead and calculate the molar mass of this. And for this lesson, the student will probably need a periodic table next to them as we go through this, and you can pause the video accordingly. So if you look up magnesium on the table, it comes in at 24.31 grams per mole. The sulfur is going to be 32.06. The oxygens are 16. But remember that there are 4 of them. So the grand total here will be 64 for the oxygens. Now that leaves us to deal with the water. All right. And again, for the oxygen, we're at 16. In water, there are 2 hydrogens, so we'll have 2 times, and on my periodic table, my hydrogen's 1.008. All right, that's a total of 2.016. So the grand total for one water molecule is going to be 18.016. Now, remember that there are 7 of these. So the 18 needs to be multiplied by 7. So for the water in this molecule, we have a total of 126.112 grams per mole that's due to the H2O. So now to calculate the molar mass of the entire compound, we're now just going to need to sum everything together. So we're going to have 24.31 for the magnesium, 32.06 for the sulfur, 64 for the oxygens, and then we're going to need to make sure to add on the water molecules. So the molar mass of the magnesium sulfate heptahydrate is 246.482, and that's grams per mole. Okay, now we'll shift next to the compound that's on the right. First, let's just review how we do the name. Now, remember that copper is a transition metal, so it has numerous different oxidation states. So this compound, we need to indicate what the oxidation state is using a Roman numeral. So we start by writing the name of the cation, so it's copper. Then we're going to need a parentheses. Now, the sulfate, SO4 that's in here, is a polyanion with a charge of -2 on it. So that means that the copper has to be +2 because we need to maintain electrical neutrality for an ionic compound. So whatever the polyanion is in terms of negative charge, the copper has to offset that exactly in magnitude but opposite in charge. So the copper is actually +2, and we're going to indicate that by using a Roman numeral 2. So it's going to be copper 2 sulfate. All right, and then we notice that for the waters there are 5 of them, and we're going to use the prefix penta for 5, and it'll be pentahydrate. Okay, remember I have more videos on my website and on my YouTube channel that deal with naming ionic compounds if this seemed rusty to you. Now, we go through the same procedure that we did for the magnesium sulfate. So we look up copper on the periodic table, and it comes in at 63.55. The sulfur, all right, is 32.06. Again, the oxygen is 16, and we've got 4 of them, so the grand total for that's going to be 64. And then our H2O, all right, there's an oxygen at 16. We're going to be adding that to the 2 hydrogens, which are at 1.008. So the grand total on the water is 18.016. Now, this is for 1 water molecule. There are 5 of them, so we're going to have 5 times 18.016. So the grand total for all the water that's in the compound is going to be 90.08 grams per mole. Now, all we need to do at this point is sum everything together. So the molar mass of the copper 2 sulfate heptahydrate is going to be 63.55 plus 32.06 plus 64 for the oxygen plus 90.08 for the waters. So the grand total here is going to be 249.69, and that'll be grams per mole. Now our last example is down near the bottom of the screen, and we see that we've got a chloride here instead of a sulfate. Technically this is barium chloride hexahydrate. Remember, barium is out of group 2, so we're not going to need a Roman numeral to indicate its charge. So the name for this one will be barium chloride. And I think what I'm going to do is just put a line here like this to indicate that these calculations belong to this hydrate. So the name of this is going to be barium chloride, and then there are 6 waters, so this will be excuse me, Hexahydrate. Hexa for the 6. Alright, so let's go ahead on this one. It's the same deal. Check on your periodic table. You see the barium is going to come in at 137.33. The chloride is 35.45, but there are 2 of them for a total of 70.9. Alright, and then again on the waters, the H2O itself is 18.016, like in the other situations. And then there are 6 of these, so we need to multiply by 6. And the total, the grand total on the water will be 108.096 grams per mole. So again, now all we need to do is add these up. So for the barium, it'll be 137.33. The chlorides total 70.9. The water totals 108.096. And the total is going to be 316.326 grams per mole. And with that, I'm going to go ahead and close the video.